how bad can this get, right? 4 p.m., talking about politics at the end of the event. Now, I won't try to convince you that politics is actually something great that we should be thinking more about, even if it's true. Like, this is just an excuse for us to talk about Bayesian inference. But I'll throw in some notes about why I think that measuring what's happening in society is also important. Not just because we have elections in the US coming soon, probably in Portugal as well, if things don't go as we want in the budget. Before I go there, like we've spent the last 2 days, a bit in LLM land as well. We've talked a lot about large language models and Gen AI. And I cannot resist mentioning that generative AI is not something new. Maybe the term, yes. But let's think that, in theory, whenever we're building a machine learning model, we want to distinguish between 2 classes of things if we're doing classification. The classical approach, the usual approach, is that we try to find a boundary between the 2 classes, what we call a discriminative approach, and that's nothing wrong about being discriminative when doing machine learning. But there's an alternative approach, which is actually trying to understand what's the process that generated the data, meaning what's the distribution of data we have, probabilistically speaking, trying to learn that, and then using that as a way to do machine learning. So I take a new data point, and I try to guess, is this more likely to have come from distribution A than distribution B? And this is actually quite powerful, because with discriminative machine learning, like you're learning the boundary between these 2 things, but you have no idea of what happens beyond those boundaries. If you're old enough to have worked with SVMs, it's exactly what they do. They learn this boundary in the feature space, but then you have no idea if you have points just closer to the border or further away. And the good thing about generative machine learning is that you model the distribution first, and then you can actually sample new data points. Whenever you're using LLMs and you take a distribution of data that the model learned and you try to generate new sentences, you're actually doing something similar as this one. And this is going to be super important for doing Bayesian inference on anything. Because in theory, and I promise this is the only slide that has formulas, and we won't be spending lots of time here again, 4 p.m., last day of the conference, we all want beers. But there's this beautiful thing about being able to talk about the world in terms of probabilities. Whenever we're trying to model something, we want to know its probability. If you're building a churn model, you want to learn the probability of churn. But it's not just the probability of churn. It's the probability of churn knowing the things you know about your company, about your customers, about the world, whatever. So you have this thing called a conditional probability, this thing you can see on the left. So what's the probability of this probability, this parameter, this theta I have here, being the true one, given the data I know? And that's something that's hard to know. And so Bayes has invented this wonderful way of reversing the problem, of saying, I don't know what's the probability of this parameter being true, but I can calculate quite easily what's the probability of seeing this data if this parameter was true. And statisticians, for some reason, seem to love coin throws. And so the usual example is, if you're trying to guess what's the probability of a given coin being fair, so if you have to say, am I going to get heads or tails? You start with this idea that maybe with this prior, this beautiful thing, this yellow thing over there, this idea that I think that it's going to be 0.5. But maybe it's a bit more or a bit less. But then you start making throws. And if you think you have a fair coin and after 10 throws you only get heads, no tails. And you start to think, well, maybe my previous assumption is not really correct. Maybe the coin is really not fair. Because the probability of seeing 10 tails with a coin that's 0.5 fair is super low. And we know how to calculate that. If you paid attention in your statistics class, you remember there's something called a binomial distribution that doesn't hurt you, but that allows you to calculate the probability of seeing this sequence of events if the probability would be 0.5 in this case. And it's going to be super low. And so you have this wonderful formula that allows you to then rethink, recalculate, given that I've seen 10 throws, all heads, what's the new good estimate of what the probability should be? This formula allows you to do that so you can basically multiply these probability distributions. The thing is, for anything that's real in the world, this is like incredibly hard to do. Multiplying probability distributions and hoping to end up with something that you can work with is basically impossible. And so the only thing that's new, you can guess that like Thomas Bayes is not a young guy from this picture. The only thing that's new here is that we've been inventing new ways of trying to estimate this, again, complex term, posterior, what's this updated probability distribution after I've seen this data. And we won't go into lots of details about how Markov chain Monte Carlo works, but basically the intuition is that you can select a probability, a number at random. So I'm going to start thinking that my coin is fair with 0.5. I'm going to see if there's a relatively high probability of seeing the data I've seen if it was actually 0.5. And then I'll try to change this number slightly. So instead of 0.5, what if I said 0.6? If the probability of seeing the data with 0.6 is higher, then I'm moving in the right direction. So I say, OK, then I'm going to think it's 0.6. Now I'll try to change it again, maybe in the opposite direction. Let me go to 0.4. And then it decreases again, the probability. And then 0.4 is not a good estimate. And I can do this a number of times, where I'll try to do different estimates, and I'll try to simulate changing the parameters. And I'll have this idea of what's the best estimate of the probability distribution of the probability of the coin being fair. All theory aside, why should we care about having an alternative way of predicting something? It's not just because it's generative, so it should be good. I think by now we all know that that's a bad approach. The most important thing is that sometimes we have small data. And people keep on selling to us that we all have lots of data, that data is the new oil. Everything is like a huge number of data points. But I'm sure that someone in your work or your exploration, your research, you've found data sets that are actually small. With election forecasting, like if you look in the past 20 years, we have like 5 general elections. So you can think of the most complex machine learning model. You can say, I'm going to use light GVM, and I'm going to use GDP, unemployment. I'm going to use the polls from the last 7 days, 30 days, 1 year. And then you'll end up with like 100 features and 5 elections to predict. And I challenge you to have a good model with 100 features and 5 rows. So we have a number of cases, with elections being one example, where the data we have is actually not that big, but also where uncertainty matters a lot. Like in classical machine learning, you're going to get something that we call a point estimate. So you're going to basically calculate the probability for a given row, and it's going to give you a number. How certain are you about that number? Well, we then have to use tricks. And then start bootstrapping, and then start to try to invent confidence intervals on top of predictions, but we're hacking it. The models are not built to give you their estimate of confidence, of how uncertain a given thing is. And sometimes it's super important to know how uncertain things are. Like we've heard conversations around causal machine learning for marketing. If you were in that session over there some hours ago, you've heard that. Like sometimes the risk of doing an action and it failing is insanely high. So in some cases, I might just say, if the uncertainty is high and the probability of hurting my business is actually above something, I prefer not to do it. The estimate could be 0.8, but if the standard deviation is like 0.6, then maybe you can make something wrong, right? So measuring and being able to see how uncertain a given prediction is might be super important. And then finally, sometimes you know things about the world. Continuing with the marketing example, if I told you I had a marketing campaign with an 80% conversion rate, you should be frowning. You should be saying, no way. I've been doing this forever. There are no campaigns with 80% probability of conversion. Those don't exist. And we know that, but whenever we train a model, we're not saying anything. We're pretending to be objective, but what we're actually doing is we're forcing the model to waste his prediction power with the number of samples we have to learn something that we already knew. That probably the conversion rate is going to be below 10%, for instance. And classical machine learning has no way of embedding this knowledge we have about the world. So we hope that the model will learn that based on interaction with data. But it's like throwing your hands in the air and hoping that the best happens. No good way of embedding actual knowledge we have about the world. We can do this a bit more in a structured way, and I could give you like 10 main differences about this. But the main ones are the ones I've shown before. Let me be honest with you. There is a main problem with using Bayesian inference, which is it's insanely costly, computationally speaking, to run things whenever you have big data. So if you have small data, this is great. If you actually have lots of data, this is probably the wrong approach. even though you can always reduce a problem of having too much data to smaller single data problems. What about elections, then? I promised I would say something about elections. Again, I've already told you why this is a great example. Very few observations. 4, 5, 6. There's no way you're going to do anything with classic machine learning. But also, it's a bit harder than that, because we know that the data we're collected is biased by definition. Pollsters are still calling people through fixed landlines and hoping that someone answers. How many of you have fixed phones at your homes? People working in telcos cannot raise their hands. No one. And that's the main way how we're conducting polls. So it's obvious that we're going to have biases. So an estimate built on top of this is not going to be great. People's preferences change over time. Sometimes they change too much, and we prefer for people to keep to previous choices. Sometimes too slow. But things change. So if I use the last 20 years to predict something, well, too bad, because something that was true 20 years ago is no longer true. For instance, we have new parties. So what do you do with that? And then you have other sources of variation of things that change. So it's a problem with lots of variation, very few observations. Why are we even wasting time trying to predict anything? Well, because even if we cannot predict anything certainly, we can at least reduce the uncertainty we have from the things we can actually measure and see. We were all surprised when Donald Trump won God knows how many years ago. Even if the polls were saying that there was like a 40% probability of that happening, because we were not paying attention to how uncertain the predictions were. So if we can actually use this to at least be able to accurately measure how uncertain a given prediction is, then maybe we can act differently. Can I ignore going to vote if I know that the probability of a candidate I really don't like winning is high? Or the prediction being super uncertain? Yeah, the other candidate is the head in the polls, but the uncertainty is huge, and maybe I shouldn't be going to the beach and I should be voting. And I'll stop here making political comments. But if I'm doing something for marketing, something for health, like, yeah, I think that this new drug I'm developing is going to be great, but the estimate of its impact ranges from like +5 years in life expectancy or -3 years. Do I really want that? Even if the average is positive? So just reducing and measuring uncertainty is a benefit in itself. With elections, we could say, yeah, we have some prior information about how many people voted for this party, so we have some expectation. We also have some expectation about the way that people change opinions. If I told you that a party today had 10% support and tomorrow 60%, again, I would expect you to frown, to say, not likely. Why? Because we have a prior expectation, prior knowledge about how the world works, about how we work. So we can say that to the model. We can tell it, it's not very likely that people are going to change opinions super quickly. So I have a prior about how quickly people change opinions. Then I can test, the thing I can actually test is, assuming that there's an underlying parameter I'm trying to estimate, which is, what's the true percentage of support that people have for a given party, or for all parties? That's the thing I want to know. How many people like party A, B, or C? I can then say, what's the probability of, whenever I call people, getting these answers, if the true proportion was like 30%? If a given party has 30% support, if I call 10 people, how many people are expecting to choose that party? Numbers. 10 people, 30%? Can you still do that at 4 p.m.? 3, thank you. If I said I got 2 answers, would you be surprised? No, that's still reasonable, and 4 is still reasonable. So we know that there's a relatively high probability of the number not matching exactly, but being close to it. And so given that we have this prior probability distribution of how things work, we're seeing polls, we can then adjust what we think is the actual vote share that's on people's minds that allows us to see these poll results or the actual election results. So let me show you how we could do this super quickly. A very simplified model. This is done in something called PyMC. It's a library for doing probabilistic programming, which is basically working with probability distributions. Through programming, again, if you were sleeping through your probability classes, now you'll regret that. but I'll try to make it as easy as possible. What we're saying is, for instance, we assume that there's a real, latent, unobservable support of each party. So if I talked with every single person in a given country, and I asked them what their preferred party was, that's the real support that that party has. That thing is unobservable. That's the thing we have over there. And I'm saying that at the beginning, I have no idea of how much that is, so I'm assuming that it's like a normal distribution and that all parties share that. But because I know that it won't be the same for all of them, I'm saying that there's going to be some standard deviation about that mean support for a given party. How much is that? I don't know, so I throw a distribution at that as well. I say, I don't know how much the standard deviation is. I'm going to say that it's also a probability distribution with a 0.5 standard deviation. That allows for a big variation in support. What I'm going to say as well is, it's not actually just like normal distributions. They're all constrained. If a party grows, another party has to decline. So at the end, it needs to sum to 0 if we're standardizing the variable. And I'm doing that saying that there's this real support share, there's this standard deviation, there's some bias, like for instance, who picks up the phone calls, and that will benefit some parties and hurt some other parties, for instance, that are more geared towards younger voters. Then what I'm going to say is that the observed share that I see in the results of the polls is the sum of these two things. So it's basically the sum of the support I see plus the bias. And then finally, the thing I was saying, if I'm only sampling 10 people, then I'm OK with seeing like a small variation, 3 to 4. If I'm sampling 100 people, then I want things to be closer to 30. If I'm sampling 1,000, then I want things even to be closer to that number. And this relationship is modeled through this distribution. It's like a multinomial distribution on steroids because we have multiple parties. That's just it. And that's it. So I'm saying that the thing I actually see, which are the results of the polls, is basically the result of having an observed share and sampling a number of voters, and that's it. Then what I do is I ask the model to try to simulate, to sample, in this case, 2,000 times, and try to find what's the combination of parameters that better fits this data. What's the real support share, what's the actual standard deviation, and what's the actual bias that best explains the data I saw in my polls. And it's going to do this 2,000 times with MCMC, the thing I showed you before. It's going to ignore the first 1,000 because the model will still be trying to find the good region of the probability distributions, but that's it. What does this give me? It gives me this. For those of you that are Portuguese or know anything about Portuguese politics, you'll recognize some of the names over here. But that's not really important. Here, what's important is, you'll see that you'll have these dots being polls. You'll have these squares being actual elections. And then you'll have these squiggly lines, which are basically individual samples from my model. And you'll see something super cool. Like, unlike other models, uncertainty here is not constant. In the cases here, for instance, where you're having an election, so you're sampling like 3 million people, the uncertainty gets super low because 3 million should be pretty close to the actual voter share or the actual support. But in places where we're far away from an election, then you actually have a quite broad distribution of possible values. You can also see here that the model is still picking up some noise. It's super unlikely that the latent support is going up and down like this. It's fine. So the model is still not learning what the latent support is. I need to do something else. I need to give it more information and say, look, I really don't believe that anyone changes their opinion that quickly. So the probability of seeing support changing by this should actually be smaller. And I can do that by tuning the parameters of the probability distributions I have. But you can see how helpful this becomes. I can capture these things. It's interpretable by definition, so I can understand what components, is it the bias, is it the time evolution, is it the latent support that's causing this prediction? And then I can have this estimate of how uncertain my prediction is, and I can simulate things. I can then simulate like 1,000 elections and calculate what's the probability of getting a given result with the data I already know. I'm stopping here at the beginning of 2024 so that you're not using this for making political bets for the next cycle. Like this cool thing I was saying, the model learns that different pollsters, for instance, have different biases for different parties. So some pollsters capture some parties better than others and have different errors. I didn't tell it that. I just told it that it's also a source of error. ignoring elections, because obviously that's not my job. I'm not working in elections. I'm not working in politics at all. This can be used for a number of different areas, especially, again, where uncertainty is important and when you don't have lots of data. If you're trying to predict sports results, you don't have that many games to try to predict. That's one problem. Things change a lot. So even if you have like years of history of football clubs, players go in and out, so it's super hard to model that. Plus, it's super important to have like an idea of how uncertain the prediction is if you want to make some bets. And like my obvious example is always doing marketing mix modeling. So if you want to know more about that, come to me at the end. People tell me that you should first, whenever you're giving a presentation, you should stick to your time, which I'm failing to do. The second thing is that you should end with an inspirational quote, which I'm also going to fail. So I selected the worst inspirational quote, something from Sarah Palin saying, "Polls, they're for strippers." And I think that's a great way to end this presentation. Thanks a lot. It was a pleasure to be here.